Hello, welcome to the Circular Economy course. This will be the first lecture of the Circular Economy course. Before we go into the lecture, let me say that we have uploaded the course contents onto the University Virtual website from which you can access the course contents. Essentially, it consists of 6 modules. 5 of it will be handled by me and 1 by Professor Wouter Achten. So the way in which we will handle the course is that we will upload video lectures into the virtual university website, which you can download and read at your own pace. I will also upload additional reading materials. Some of it is mandatory, so please read them. Some of it is optional, but I highly encourage you to read these materials as well. And we will arrange separate Teams meeting in which you can ask your questions, doubts, share your thoughts, and we will also have some quizzes. So don't worry, the quizzes are not going to be graded, but it's essentially to have fun and to see whether or not you have already learned the material that has been uploaded in the past. So before we go on to the first lecture, let me say that the course Circular Economy will be essentially about making you to think about it and making you curious about the subject rather than me handing you a set of notes or documents so that you have to memorize. So we will have discussions about circular economy as a concept from various different angles. We will have discussions about circular business models, an in-depth look into recycling and various aspects of recycling. We will have a talk about legislations and policies that are relevant to circular economy, but also an entire lecture will be dedicated to criticisms of circular economy. So you'll not just see the aspects that are put forward by various different schools of thoughts for circular economy, but we will also see the schools of thoughts that are critical of circular economy and then examine those as well. So the goal or the objective of the course in a very broad way is to make you curious and then to pose questions on various different aspects of circular economy and then try to answer them by reading various materials. So the first lecture will be on the linear economy, and the first part of the first lecture will be dealing with the planetary boundaries. First of all, what is the linear economy and what are its challenges or problems? Usually it's defined as take, make and dispose. That is, you extract something from the ores or somewhere else, and then you produce the product and you distribute the product, and somewhere else it's consumed and then it's just disposed. So this is the paradigm or how linear economy is defined. So circular economy tries to challenge this paradigm or to build a new one instead of the linear economy. Let's first pause here and ask serious questions. Why can't we just take, make and dispose? Why can't we keep doing what we are doing? So the answer to that people put forth is that it has pressures on the environment. Then the question to ask is, what kind of pressures can we actually quantify those pressures? That's the first question to ask. The second is the debate about the limitedness or the scarcity of the resources. Then when we put forth the limitedness or the scarcity of the resources, then comes also the question of equitable distribution. So there are, let's say, two broad challenges in which the linear economy puts forward itself. The first is to quantify the environmental pressures of the linear economy. And the second is to see the distribution that happens within the linear economy. So if we can actually try to quantify these things, then we can talk about meaningfully resolving these challenges by a different set of paradigm. So this lecture will essentially talk about the concept of planetary boundaries. The second part of the lectures will talk about the concept of footprints. So let's move on to planetary boundaries. So the concept of planetary boundaries was introduced by the group of Professor Rockstrom in the year of 2009 in an article in Nature. So essentially his framework is this. We have the Earth itself behaving in a system. So they define an Earth system because we have on a planetary scale the hydrological cycle, the carbon cycle and whatnot. So for the past 10,000 years or so, we have this Holocene epoch in which we have, let's say, a reasonable amount of stability. But due to the human actions, a lot of these cycles have been affected. So the idea is to have a sort of definition of these boundaries, sort of these biophysical boundaries, and defining the pressures in which if you go beyond those boundaries, we can have disastrous or deleterious consequences. So the idea is to quantitatively, as much as they can, define planetary boundaries. So you see this diagram in which they defined 9 different planetary boundaries. They had climate change, ocean acidification, land use, and the global or the ozone depletion, and so on and so forth. So they had these 9 planetary boundaries, and they set control variables. So the control variables they set is not exactly at the threshold. So if you breach it, then you go into the danger. But they set the control variables a bit away from the threshold. So it makes sense. You have a buffer in which you have this safe operating space. So this is the article they published in 2009, and they updated it with an article in 2015 in Science. So here you could already see there are like 3-4 breaches here with climate change and the biogeochemical cycles. But essentially they updated with an article in Science in 2015. So you could see the 9 different planetary boundaries already here, and then what are the control variables and what is the planetary boundaries, including the zone of uncertainty, and then what's the state of the current variables. So you could already see that amongst these 9 there are 4 breaches, that is we are living beyond these boundaries already. So you have the climate change breach, the land system change is already breached, and you have the biosphere integrity that is already breached, and the biogeochemical flows is also already breached according to the group of Professor Rockstrom. So we are going to see among these 3 of them in a little bit more detail. The first is the climate change, and then we are going to talk about ocean acidification, and the third we are going to also see a little bit about the biogeochemical flows. One thing that you have to remember is that these planetary boundaries are not some sort of floating independent entities, but they are tightly bound with each other. So the change in one is going to affect sometimes profoundly a change in another. So it's in a way that it is completely or more or less really tightly interconnected, and we are going to see examples of how they are interconnected as well. Let's start with the planetary boundary of climate change. As we all know, human activities after the Industrial Revolution has resulted in increase of the atmospheric CO2, and currently it is at the level of 450 ppm actually. So one of the articles came out in the magazine Science, talks about the human imperative to limit the global mean surface temperature rise to 1.5 degrees Celsius. Why do they say that? The IPCC reports currently, the Intergovernmental Panel on Climate Change, has also called for limiting the GMST to 1.5 degrees Celsius. Here they argue that even at 1 degree Celsius, we have started to feel this change. So you see the intensity of the Mediterranean fires getting higher, and the frequency as well, and the West Antarctica ice sheets are melting in the B, and then you have low-lying regions such as Maldives experiencing increased flooding due to sea level rise, and then you have the migration of birds and insects due to the 1 degree Celsius rise that we already have from the pre-industrial levels. So their important contribution is that they have compiled a lot of information of stresses due to 1.5 or 2 or 3 degrees Celsius rise for various different systems. Hotspots are basically the regions which are having a greater risk, let's say. You could go through the whole of the article to find out the different effects of warming to 1.5 or less to 2 to 3 degrees Celsius. And you could already see that if you have a 3 degrees Celsius warming, the Arctic is going to be completely free of ice. And then you have at 2.5 degrees Celsius, even there is going to be irreversible damage for the coral reef system, and then there is so much more that you can actually read. The other important consequence is also really unprecedented, intense, and also frequent heat waves. You also see here the concept of tipping points. Tipping points are basically critical thresholds, and if you exceed that, you can have really disastrous consequences. Once again, they say that what happens if you have sort of the tipping points for various different systems, and for instance, one of the things is that you can have a collapse of permafrost even. And the important thing to note here is that even below 1.5 degrees Celsius, there are, let's say, some risks. But once we exceed 1.5 and if we are going to 2 degrees Celsius, there are substantial risks, and 3 degrees Celsius is quite extreme already. So my question to you would be is to see from various reports from IPCC and from everything else to see on which path we are on, like what they call as business as usual, and to see what kind of reduction we need to go to net zero. So this would be a sort of homework for you to work yourself and to see what kind of reduction or mitigation pathways we need to achieve a sort of a safe space. This is an interesting slide from Professor Rockström himself, who proposed the planetary boundary. So we are at 450 ppm, and he took an IPCC graph, and the claim is that at 450 degrees ppm of CO2 atmospheric concentration, the probability to reach 6 degrees Celsius of warming is 1.6%. So the first thing is to note that 6 degrees Celsius of warming of the planet is catastrophic. It is not an habitable planet at all. So it is a significant breach of the planetary boundaries. You have to remember that Rockström proposed a planetary boundary control variable for CO2 at 350 for this precise reason, because one of the things he explains is that if we have, let's say, 1.6 or 1.8 probability, how does it translate into us understanding the risks? It is almost having like 1,500 flight accidents with the number of flights we have in this day. I don't think anybody would deem that acceptable. So that is an example Professor Rockström uses to explain the risks we have now, which essentially means that you have to already put the boundary at 350 ppm, which is a safer threshold than where we are now. So you also always have to have this buffer region, which is called as this safe space. So this would sum up our lecture on the topic on the climate change alone. So it is interesting for you to look at how the planetary boundary is calculated for the CO2 atmospheric concentration, and also to look back and go and read critical articles from IPCC and elsewhere to note that where we are actually in terms of the GMST and how much of CO2 can we still emit so that we can limit sort of catastrophic damage of going beyond 1.5 degrees Celsius. So that is for you to work out yourself and to learn. So we now come to the other planetary boundary, the biogeochemical cycles. Two of them are emphasized in the PB framework. One is the nitrogen cycle and the other is the phosphorus cycle. But you also have the carbon cycle, which is kind of encapsulated inside the climate change framework. I encourage you to go to Khan Academy to check out the fundamentals of nitrogen and phosphorus cycle in case if you forgot, but they are fairly easy and straightforward. So the reason why I chose this particular boundary to investigation or to have a conversation is this. The first thing is obviously the consequences. They are, if you have the increased nitrogen, you have the increase in turbidity in fresh waters, and you have the nitrous oxides, which is also a GHG. So you can understand the consequences of them. And then you have the phosphorus cycle. And one thing you have to note down here carefully is that in their updated version in 2015, the Rockström group broke down the planetary boundary onto regional levels. So it is not only the global control variable they are talking about, which is for the phosphorus cycle, gives you the sort of probability towards anoxic events. So anoxic events refers to huge depletion of dissolved oxygen in the ocean, which can have quite disastrous consequences based on the events in the past. But these are not commonly occurring events. What they say is that you have the sort of this increased phosphorus gives you the probability to move towards these anoxic events, which should be avoided, of course, at all cost. But what is also very important for you to note is the regional boundary that they have specified here. So especially for the freshwater flows, to sort of combat the phenomenon of eutrophication, they have given a regional control variable as well to note that where we are currently at the moment. So they have this, they also talk about a regional boundary with respect to nitrogen, especially the argument is that you have the excess nitrogen, especially in the high fertilizer zones or the highly crop production zones. So if you have a redistribution of nitrogen from these intense zones to other ones, you can have much less impact, is their argument. So essentially the thing to notice here is that you have planetary boundaries with control variable and to show where we stand currently, not just on global scale but also on regional scales as well, linking to very particular phenomena, for instance eutrophication or to that of the agricultural redistribution. So the next planetary boundary we are going to see is ocean acidification. Oceans act as sort of sinks which absorb the carbon dioxide from the atmosphere. So they react with water in the ocean to form carbonic acid in the first step. After carbonic acid is formed, you have a dissociation reaction forming protons and bicarbonate ions. So these bicarbonate ions again dissociate and form protons and the carbonate ions. So you could see the protons in either end of this equation contributes to the ocean acidification. So from the pre-industrial levels, we already have a decrease of pH from 8.2 to 8.1. It doesn't seem a lot, but you have to remember that pH is in the logarithmic scale, which means we have almost a change of 30% of acidity. So that is a lot. So the other thing that you have to see is the plot on the right hand side, and you could see higher the pH, you have more carbonate ions, and then with more acidification, you have a result of bicarbonate ions. And if you have at the extreme pH end, you have the carbon dioxide. So you always have this complicated buffer equation between the bicarbonates and carbonates, which essentially results in the dissolution of the carbonate ions, which is one of the reasons why the control variable for the planetary boundary for ocean acidification is actually the aragonite saturation. It's quite simple. Aragonite is one form of calcium carbonate, and they give the gamma value by simply the solubility product. And you could see the more the carbonate reduces by dissolving, you have sort of loss of this aragonite in this ocean, which could have apparently multiple different effects. For instance, you have these sort of calcifying organisms which have the shells from the calcium carbonate, and then once you have the decrease of those things, then you have disappearance or sort of reduction of these organisms. And also the vibrant coral reefs ecosystems are under trouble once you have sort of acidification of the pH. So two things to note here is that the value, the control variable for the value is almost more or less 80% of that of the pre-industrial levels, but we have reached it now. It is almost at 84%. But if the CO2 atmospheric concentration is at 350 ppm, which is the planetary boundary for the climate change, then if we have maintained at 350 ppm, the transgression of ocean acidification boundary would not have happened. So this indicates an important phenomenon. Planetary boundaries are not independent entities, but they are closely interlinked to each other. So the underlying actual boundary here is the atmospheric CO2 concentration for ocean acidification as well. Granted, it is expressed in a different term, say aragonite saturation, but essentially it's also about the atmospheric CO2 concentration. So we have a huge increase from the pre-industrial level, which is why we are where we are. So you have to note also importantly the interconnectivity between different planetary boundaries. So we come to the last part of the lecture. Thus far we saw planetary boundaries, quantified ones, and we saw some of the planetary boundaries are already being transgressed. Then we ask ourselves the question, if there are planetary boundaries that we as a species are transgressing, and if we are having a sort of this environmental pressure that we are talking about, and also awaiting disastrous consequence if we are going to transgress these environmental boundaries, then how are we going to handle the economy as a species in general? This is a highly contentious and debated topic. So we are going to deal a lot of it in the module where we talk about criticisms of circular economy. But mostly I would point to you to the fact that the word growth is going to be thrown around a lot in a lot of different ways. Growth, neoclassical growth, green growth, degrowth, and so on and so forth. So we are going to take a deeper look into the concepts of growth. But for now, I would put that aside and just focus on one study that got recently published by the Steinberger group in Nature Sustainability. So Professor Rockstrom calls, to be honest, the neoclassical economics as sort of Mickey Mouse economy. So he says that thus far the postulates are that we are going to have growth at the expense of natural capital, which is the land and stocks, etc. And this economic worldview is something that needs to be challenged. In Professor Rockstrom's opinion, he calls it Mickey Mouse economy. So what they argue for and what they advocate for is to incorporate the societal component to it. So then comes the sustainable development goals and the concepts of intergenerational equity, because we have a limited finite planet, so how we are going to leave it to the next generation also becomes a question. And the group of Professor Steinberger advocates this concept of safe and just space. So it is a combination between the planetary boundaries and also fixing societal boundaries. So the question they asked is that how is resource use connected to social outcomes? For instance, whatever natural biogeochemical cycles we have, or the land use and energy use related to, let's say, social developments such as education, technology, manufacturing, and the outcomes such as what is our life satisfaction, what is our health outcome, health expectancy, and how far are we in general satisfied with life. So this is sort of advocating within a needs framework, that is, you have as a species very important universal needs. Of course, it changes with geography and culture, but there are universal needs that could be identified. So they try to understand the interaction not just in one way, but both the loops, both resource use and provisioning systems and social outcomes in all different ways. And what do they find? So this is the sort of graph that they have produced. It's consistent with the concept that's called as donut economics. So I encourage you to go and read about this sort of ecological economics as well. But it simply states this: you have the inner circle, that is the social threshold, and you have the life satisfaction, nutrition, sanitation, whatnot inside the social threshold. So at the right at the center point is the worst possible outcome. That is, you have the worst possible social indicators. And once the blue line goes far and then fills the circle is when you have satisfied social indicators. That is, you have reasonable education, social support, and democratic equality, and so on and so forth. And you have the biophysical boundaries. So the biophysical boundary that we talked about, the planetary boundary, is at the outside, and we have to see how much of the social needs are satisfied while at the same time not transgressing the planetary boundaries. The left hand side is for US and the right is for Sri Lanka. So for the left, you could see there are social thresholds are reasonably being satisfied, while the biophysical boundaries are just getting exceeded than what is an acceptable planetary boundary limit. Whereas for the Sri Lanka, you could see that the social thresholds in not a lot of cases is being going beyond the biophysical boundary. In fact, it's staying well within. You have some satisfaction in some social thresholds, but not complete satisfaction. Here I have to pause and say something. The social threshold, they have quantitative limits here. These are, let's say, opinions. These are not hardcore scientific limits or something. These are debatable. For instance, they take a poverty line of $1.9 per day. That's something you could debate with. So in this study, in this slide, you have the results from their study. On the left, you have the percentage of countries which have exceeded the biophysical boundaries. On the right, you have the social thresholds and the countries which are yet to reach the social thresholds. You have to see that the thresholds are, let's say, arbitrary. They are not fixed in stone. But one thing you have to notice very carefully here is that they were able to scale down the planetary boundaries to that of countries. That's how they were able to perform the study, because they were able to compare between countries, because they took the planetary boundaries and they fixed it for per capita boundary for individual countries, and then they were able to have the study. So in a nutshell, their conclusion is that the models such as Sustainable Development Goals for the UN pursue economic growth as the most important phenomenon, and this, in their opinion, puts at odds the transgression of biophysical boundaries. That is, according to them, it's much better to pursue things such as human well-being and happiness instead of, let's say, a metric of GDP growth. This is, in a nutshell, their conclusion. But this is a debate we are going to see in the future a lot more in other parts of the lecture. One thing I will say while concluding this lecture is that you see the challenges with the linear economy is not just the component of environment, that is the different planetary boundaries, but already serious scientists, it could be from various different parts of the world, who deal with the framework of planetary boundaries, talk a lot about the social component as well. So an alternative to linear economy paradigm has to answer both these very challenging questions. So having this in mind, I encourage you to listen to the other important biophysical measurement, that is footprints, in the second lecture.